I'd like to talk about a couple more electrophilic addition reactions. And we're starting with trans-2-butene. These electrophilic addition reactions involve the addition of water and alcohols to alkenes. These reactions are acid catalyzed. You'll often see the catalyst for a reaction written over the reaction arrow. I told you in our last video that you will often see the solvent underneath the arrow. Well, we put the catalyst over the arrow. In our first example, our product is going to be an alcohol, and in our second example, our product is going to be an ether. So let me draw the groups that I'm adding for you in red. In the first example, as I said, we have an alcohol as our product, and in the second example, we have an ether as our product. The reaction mechanism you're going to see is very similar to the mechanism that I showed you for the addition of hydrogen halides. In fact, there are parts of the mechanism that are identical. There are a couple of additional steps that involve the catalyst. So let's go ahead and get started looking at our mechanism. Let's look first at the addition of water. Our first step is identical to the first step in the addition of hydrogen halides. H+, or if I'm doing the reaction in water, hydronium ion is acting as the electrophile, and it's going to attack that double bond. It's going to grab a pair of electrons from my alkene, and this is going to generate my same intermediate that we saw before. This is an equilibrium reaction. That's why I'm using the equilibrium arrows. My intermediate is a carbocation, the exact same intermediate that we saw with the addition of hydrogen halides. What is my next step? You may remember that the next step involves the combination of a nucleophile and an electrophile. Well, do I have a nucleophile? Yeah, as a matter of fact, I do. I have water floating around in this reaction. Remember, the oxygen atom of water has two lone pairs of electrons. So water can act like a nucleophile. It's going to come along and it's going to donate one of those lone pairs of electrons to that carbocation, or to that carbon that has the positive charge. This is going to give me a new intermediate. Now my oxygen has 3 bonds. What this means is that my oxygen is going to have a positive charge. And let me just erase this and draw both of my hydrogens. Now I still have water floating around in this reaction. And remember that water can act like a base. This intermediate here has a name. This is called an oxonium ion. And that is an oxygen that has a positive charge. My water is going to act like a base, and it is going to capture one of those protons that's attached to my oxonium ion. And what's going to happen next? I'm going to generate my alcohol product plus H3O. You'll recall that because this reaction is acid catalyzed, I started with H+. Let me go back to the beginning of this reaction. We started with H+ right here, and I said that that could be H+ or that could be hydronium ion. And we're regenerating hydronium ion. So the H+ is not being consumed, it's just being used as a catalyst. Let's look at our second mechanism. And again, the first step is identical to the one that we just saw. We begin with electrophilic attack on the alkene by the proton, or it could be hydronium ion, and we're going to generate a carbocation intermediate. You may recall our next step is the combination of the carbocation intermediate with some nucleophile, and in this case the nucleophile that we have in solution is methanol. Methanol is going to behave just like water did in the last reaction mechanism that you saw. So methanol is going to donate a pair of electrons to that carbocation, and I'm going to generate a new intermediate. So now I've formed a bond between the carbon that was the carbocation and the oxygen of methanol, and I've generated again an oxonium ion. That's an intermediate where an oxygen has a positive charge. You may recall that in our last mechanism, the next step was the abstraction of a proton by a base. The base that I have floating around here in solution is methanol again. So methanol is going to donate a pair of electrons to that proton and abstract that proton. This is going to give us our product, which is an ether. It is a methyl ether, and it's going to give us CH3OH2 plus. You see that I now have another oxonium ion, and basically I have regenerated my acid catalyst in the form of an oxonium ion. So far we've seen 3 electrophilic addition reactions, and let's just take a moment to compare those 3 reactions and see how they're the same and how they're different. Each of these 3 reactions begins with the same first step, and that is the electrophilic attack by a proton, or by some electrophile, on the alkene with the generation of a carbocation intermediate. The next step for each of these reactions is the combination of our carbocation with some nucleophile. In the case of the addition of hydrogen halides, that nucleophile is going to be the halide anion. In the case of the addition of water, that nucleophile is going to be a molecule of water. And in the case of the addition of alcohols, that nucleophile is going to be your alcohol molecule. You'll note that in the case of the addition of the halides, we have a positive charge and a negative charge coming together, and that neutralizes the charges, so our product is neutral. In the second 2 reactions, we see we have a positively charged species combining with a neutral species. The result of that combination is going to have to be positively charged. Remember that we have to conserve the charge on either side of the reaction. So in the case of the addition of hydrogen halides to give us an alkyl halide, we're done. In the other 2 examples, there is an additional step that has to take place, and that additional step is the abstraction of H+, a proton, from the intermediate oxonium ion, and that could be water or that could be methanol acting as the base. This gives us our final product, which in this particular example is an alcohol, and in our next example is an ether. I hope you can see the similarities between these 3 reactions because they are very much alike. You may recall that in the addition of hydrogen halides to alkenes, Markovnikov's rule applied. And in Markovnikov's rule, remember that we said that the protons will go to the carbon that already has the most protons. Or another way to say that is that the nucleophile will go to the most substituted carbon to give us our major product. In the addition of water and alcohol, since the first step is the same, the formation of the carbocation intermediate, and it is this step that determines the ratio of the major and the minor products, Markovnikov's rule is also going to apply in these other electrophilic additions as well. So we see the same distribution of the major and minor products. Or in other words, for the major product, the nucleophile will end up on the most substituted carbon because that product originates from the more stable carbocation. See if you can figure out what the major and minor products would be from these 2 addition reactions. Go ahead and pause the video, and once you have it figured out, start it back up again. Hopefully, you identified these products as the major and the minor products for these 2 reactions. A couple of things that I want to remind you about, and that is that we have on the top of our reaction arrow our catalyst and actually one of our reagents, and you'll see that we organic chemists sometimes write our reactions this way, and you'll see underneath the arrow the solvent that we use. I also want to point out to you that typically organic chemists do not balance their reactions, and this is largely because we often have mixtures of products. So if you look at these reactions up here, you can see that obviously they are not balanced. New organic chemistry students are usually very troubled by this because you spend so much time in general chemistry trying to balance reactions. The other thing that you will often see is that we often do not write down the inorganic byproducts of a reaction. We're just more worried about the organic portions of the reaction, and we kind of forget about inorganic parts, especially if those things are just acting as spectators. For instance, a spectator ion that's not really participating in the reaction at all. Don't get too hung up on that either. What about this reaction? We have the acid-catalyzed addition of ethanol, an alcohol, to 2-pentene. This reaction is going to give us two products, 2-pentanol and 3-pentanol. Which one of these is going to be major and which one is going to be minor? Well, it turns out that in this particular reaction, because both of these products originate from a secondary carbocation, you're probably going to have a pretty equal distribution between these two products. One of these products is not going to be favored over the other. If 2-pentanol is your desired product, a better way to do this reaction is to begin with 1-pentene. 1-pentene is going to give you 2-pentanol as the major product and 1-pentanol as the minor product. If your desired product is 3-pentanol, you probably want to look for a different way to make this alcohol, and there are many, many other ways to make alcohols. We're just not going to cover them in this class. I hope you found this video on the comparison of 3 different electrophilic addition reactions helpful.